Okay, so now that we have these properties of triangles involving perimeter, area, similar triangles, and Pythagorean theorem, let's put it all together into some word problems here. So this first scenario, Anna and Emmanuel start at the same intersection. Anna is going to walk east at 4 miles per hour, while Emmanuel is going to walk south 3 miles per hour. They are communicating with a two-way radio that has a range of 2 miles, and with that, how long after they start walking will they fall out of radio contact? Okay, so let's see, we're going east and south here, so let's put the intersection right here. I'm just going to draw myself a little picture. So we have Anna is walking east at 4 miles per hour. And we have Emmanuel's walking south at 3 miles per hour. And what we want to do is see when they're out of communication or when they're going to lose communication, which would be a distance. So Emmanuel would be standing here, Anna here, and that distance we want to be 2 miles. Okay, so something I'm noticing here is we have a right angle. So Pythagorean theorem is a possibility here. What's also important to notice is we have different types of units here. We have rates for 2 side lengths and a distance for the other side length. So distance and rate, and then we're actually asking how long, so time is going to be at play. So we are going to be bringing in our DIRT formula. Distance equals rate times time. And what I need to do is I need to think about this picture, but all in the same units. So what I'm going to do is redraw this a bit. And what I need to do is either put everything's in terms of a rate or everything in terms of a distance, which let's go ahead and put everything in terms of a distance. So let's keep that as 2 miles. But then, and actually, let's label these. So this is a distance, this is a rate, this is a rate. So if I wanted to change that 4 miles per hour into a distance, I just need to multiply by time. And then same thing with the 3 miles per hour, I would need to multiply, and it should be the same amount of time that they're walking, so it'll be that same variable of t. So what I'm going to do is rewrite this as where I had 4 miles per hour before. I'm going to take that rate times time, and now that would be as a distance. Same thing with the 3 miles per hour. Now I'm going to write that as 3t, and we'll call that miles. And now we have our Pythagorean theorem that we can set up and start solving, and we're going to be solving for time. So we have our hypotenuse is the, didn't want to do that. Let's highlight the 2 because that is our hypotenuse. So that's going to go on one side all alone, and then equals legs squared, and we want to use our parentheses here because everything's getting squared. And same thing with 4t. So we're going to have 4 equals 9t squared plus 16t squared, which 4 equals 9 plus 16 is 25, t squared. Divide both sides by 25, so t squared is equal to 4 divided by 25. And we're going to take the square root of both sides to get t equals 2/5, or 0.4. So our final answer here, we're getting a time of 0.4 hours. So how long after they start walking will they fall out of radio contact? After 0.4 hours. If you wanted to change this into minutes, what you could do is just multiply by 60. That would be our conversion here. So then we could see that it would be the equivalent of 24 minutes if you wanted to write it that way. 0.4 hours is totally fine. Just sometimes feels wrong to write hours as a fraction or a decimal, so you can always convert between the two. Just make sure you don't change 0.4 hours to 40 minutes because it's not base 100, it's base 60, so you want to be careful there. Okay, so there's one case where we used our Pythagorean theorem along with our distance equals rate times time formula. Let's look at another case. We have the roof of an A-frame ski chalet forms an isosceles triangle with the floor. So what that means is, if you haven't seen an A-frame before, it just looks like a big triangle. And what makes it isosceles is that the two base angles are the same measurement. And what that forces, or what that does rather, is it makes two equivalent side lengths. So those two side lengths are going to be the same distance. The floor of the chalet is 24 feet wide. And the ceiling is 20 feet tall at the center. So what I'm going to do is draw the height here, because our height makes a right angle, and that height there is 20 feet. Okay, we're going to build a loft, and what that loft is going to look like is it's going to go across here. It's going to split up the middle of, or not middle, but it's going to split up our triangle. But what we're going to have here are similar triangles. That angle is going to be the same as that angle. That one's the same. And then this is a shared angle, which is definitely the same. So some similar triangles occurring here. And we have a loft is built at a height of 8 feet from the floor. So we're going to have this distance be 8 feet, which means that remaining distance is going to need to be 12 feet. This is not drawn to scale, but it's really about the numbers. That's what we're worried about. Okay, so, and did I miss any other information? How wide will the loft be? So what we want to know is, what is this distance here across the floor of the loft? Okay, so our two triangles. We have our big triangle and we have our smaller triangle. And we have 20 feet here, and for the, 24 feet there, sorry. And then for the height, we have 20 feet. And then for the loft, we have a height of 12 feet. And we don't know what that bottom distance is. That's what we want to solve for. So, similar triangles. We can make a ratio of those side lengths along with a ratio of the heights. So, let's go 20 to 12 is equal to 24 to x. And then we can do our cross multiplication. So bring down the equal sign. 20 times x is equal to 12 times 24, which is 288. Divide by 20 for 14.4. And that would be in feet. Okay, so that one, it's a matter of setting up a picture and seeing that we have similar triangles, and then with that we can set up the ratios of our similar triangles to solve. Okay, this next one, a big one. Leanne is sailing 3 miles west and 5 miles south of the harbor. let's go ahead and get a picture going. So we're going west and south. So let's go, here's our starting point. Let's put it more in the middle here. Okay, 3 miles west, 5 miles south, and here's the harbor, and this is where Leanne is ending up. She heads directly towards an island that is 8 miles west and 7 miles north of the harbor. Yep, here's where my picture is flawed, but we'll make it. Let's try it again. Let's try it again. Okay. The harbor. 3 miles, 5 miles. Here's the harbor. Here's Leanne. And then the island is 8 miles west and 7 miles north of the harbor. So we're going to go over and up. So let's see, 8 miles west. So we're going to go 5 miles further. Let's put a 5 there. So we have a total distance of 8. And then we're going north 7 miles. And that's where the island is. Okay. There's our picture. Not too bad, but not too great either. Okay. How far is Leanne from the island? So we want to find this distance here. Let's just change the color of that to make it nice and bright. Okay, we want that distance right there. So what we need to do is try to make a triangle that uses that side length. Right now we have these kind of 2 separated triangles. That doesn't help us too much because we don't know where that 5 is being divided. So instead what we can do is we can try to form a big triangle. And what I'm seeing is I can either go that way, which works, or this way, which also works. So let's just choose one of them. Let's say I go like this. So we have that side length of 7, but then that's a distance of 5 right there. So really this total side length here, 7 plus 5, which is 12. And then along here on the bottom would be a distance of 5. So what we have here is a nice right triangle, and we have 2 side lengths, 12 and 5. So if I want to find that missing side length, I can use the Pythagorean theorem. So our missing side length is the hypotenuse, so I'm going to have x squared is equal to 12 squared plus 5 squared. And then we'll just take the square root of both sides, and let's go ahead and plug that into the calculator. Okay, so we are taking the square root of 12 squared plus 5 squared, which is 13. So Leanne is 13 miles from the island. Okay. How far will Leanne be from the harbor when she is halfway to the island? Okay. So what we're doing here, I'm going to just clean up our picture a little bit. Get that out of there. And what we're going to do is cut that distance in half. And that isn't necessarily happening right here. It might be kind of more here-ish. It's not great, but not terrible either. I am gonna, let's just leave that there. Okay, so with that, we cut that distance in half. And the distance that we're interested in is from that point there, that halfway point, and the harbor, which is back here. So what I'm thinking of is, if I kind of zoom in here, is if I drop a perpendicular, that's going to help me solve for this hypotenuse. This is now our unknown. So we have these 2 side lengths here. We have this height and we have this length here. Now this length isn't going to be too bad because we'll have that 3 right there. Plus this 5 is going to be nicely divided in half. And just to give you a visual, what I'm going to do is grab some pieces here, and what I want to visualize is this diagonal. What's going to help is kind of visualizing this rectangle that diagonal is going through. So let's just, as kind of a separated picture here, let's go like this, where we have that going across. And we had the side lengths of 5, and 7 plus 5 is 12 for those two. And what we're doing is we're going halfway. Now when we do that, when we cut in half, it is cutting the 5s in half. It's also cutting the 12s in half. So when we get to that halfway point, we end up with these separated measurements like 6 and 6, 2.5 and 2.5, 6 and 6, 2.5 and 2.5. So that's what we're getting when we cut in half. So to go back to our picture here, what we're going to have is along that bottom piece, let's just rewrite this, where we have the 3 right there, that 5 is now going to be cut up in half. So we have 2.5 and 2.5 right there. So with that, we're getting this bottom distance, 2.5 plus 3, so we're getting a 5.5 down there. In fact, let's just kind of grab that green triangle that I'm working with so that we can see it separated. So now we know that is 5.5. Now, that height there, it's a little tricky, but what we could think of is when we cut in half, we have this distance of 6 and distance of 6 down here as well, which if 5 is covered up by this piece here, our leftover is a distance of 1. So just putting the puzzle pieces together using the fact that we're kind of dividing up that rectangle in half. So if we kind of zoom out and just to give us our visual, this is where our rectangle is. So we could see that cutting point made those two distances of 6. So we had that missing distance of 1 right there. Okay, so our right triangle is a 1 and 5.5. So with that, we're looking for that distance of the hypotenuse, and that's coming from 1 squared plus 5.5 squared. And then we'll take the square root. Okay, so plugging into the calculator, the square root of 1 squared plus 5.5 squared is 5.59. And that is in miles. Okay, that one's pretty tricky and has lots of pieces to it. There are other ways to do it where you could bring it to a coordinate system to help out. But really it's just getting a good picture going and then thinking about the properties of these triangles and various shapes to get to using the Pythagorean theorem or similar triangles if we should need it.